ठीक है, अभी जाके कल भी कह रहे थे ये वाले की कल भी परसों आ रहे थे फ़ोन किया था मनीष जी कह रहे थे आप ये वाले इधर घूमते रहते हैं हम आपको लेके चलेंगे आपको और खाना बना के आप सब खाने को मिलता और सोचिए आप भी आइए उन्होंने जब मैं स्कूल से निकला तब उन्होंने फ़ोन किया आर यू कमिंग तो उनको लिख के दिया आप उन्होंने सब लिख के दिया कल वो ऐसा ऐसा 12:30 बजे
फिर वो दिक्कत हो गई आपकी
ये तो
हम भी बोलूँ सर
हम बोलो ये बोल पुराना वाला वहाँ देख रहे हो बस यहाँ बैठेंगे. Good morning, learners and viewers. Welcome to the session for Quantitative Analysis for Managerial Application, MMPC 005. Today we will be talking about Block 3, which is sampling and sampling distribution. There are 4 units in it: sampling methods, sampling distributions, testing of hypotheses, and chi-square test. So we will be starting with Unit 9, that is sampling methods. Well, one is interested in measuring some attributes of a large or infinite group of elements by studying only a part of that group. This process of interfering something about a large group of elements by studying only a part of it is referred to as sampling. Now we will take up an example, suppose of Bank of India. We have to measure the level of employee motivation. We administer a questionnaire to 250 employees from different branches and offices all over the country out of its 30,000 employees. Now, there are some definitions what we will be referring to the later part of this session. So we will start with population. It is collection of all elements about which some inference is to be made is known as population. Any characteristic of a population will be referred to as a parameter of the population. Some population parameters is inferred by studying only a part of the population, that is sample. And any characteristic of a sample is called statistic. Now, we'll see to this diagram. We can see that there is a rectangular part which is marked with yellow color. That is a whole, if you take that rectangle, that is the population of 30,000 employees. Here what we have to study, that is the static motivation level of the sample. Now, where is the sample size? The blue marking is 250 employees, that is the sample size. And there is another component that is parameter. That is the study of motivation level of the population. And another component is Celsius, or the complete enumeration of the population. There are different modifications, symbols, which are used to So two different things, that is the population as well as the sample. If we talk in terms of population, there is the basic parameter is there. Population size is denoted by capital N. Population mean is denoted by mean. Sample standard deviation is by sigma, and sample proportion is by capital P. On the other side, if we talk about in terms of the sample, here the parameter changes to statistic, population size changes to sample size, population mean changes to sample mean, that's x bar now. Sample standard deviation is given by S and sample population by small. Now, what is the need of sampling? It is to study the time taken for the study, cost involved for the study, physical impossibility of complete enumeration, practical infeasibility of complete enumeration, and enough reliability of inferences based on sampling and quality of data collected. Now, another part is what are the different types of sampling. There are two basic types of sampling depending on who or what is allowed to cover the selection of the sample. First one is probability sampling. Here, each element in the population has some non-zero probability of getting included in the sample. And the second one is non-probability sampling. Here, samples are picked up based on the judgment or convenience of the enumerator. What are the different methods of probability sampling? First one is simple random sampling. Second one is systematic sampling. Third one is stratified sampling. The fourth one is cluster sampling. We will start with simple random sampling. Under simple random sampling, each element of the population has an equal probability of getting included in the sample. If anything can be picked. All other forms of probability sampling use this basic concept of simple random sampling, but applied to a part of the population at a time and not to the whole of the population. Then we are using the word probability. No doubt we are aware of the probability because we have read it in the earlier sessions. Now here we will be talking in this probability about the in case of sampling. In general, there are NCN different samples of size n that can be picked from a population of size capital N. There we used NCR. Simple random sampling ensures that any of these samples has the same probability of being picked up. For example, 1 upon NCN. Then comes your systematic sampling. Systematic sampling proceeds by picking up one element after a fixed interval depending upon the sampling ratio. Suppose we have a sample of size 10 from a population of size 100. That means our sampling ratio would be small n by capital N, that will be 10 by 100, that means 1 by 10. We will decide where to start from among the first 10 names of our friend. That means if we started from the seventh element. The first element will be 7, then after a gap of 10, the another one, second one is 17, 27, until 97. So that means we will always have a gap of 10. Then comes stratified sampling. The basic idea behind the stratified sampling is to divide the whole heterogeneous population into smaller groups of subpopulation such that the sampling unit are homogeneous with respect to the characteristics under study within the subpopulation and heterogeneous with respect to the characteristics under study between or among the subpopulations. Such subpopulations are termed as strata. Treat each subpopulation as a separate population and draw a sample by SRS from each strata. Stratified random sampling is a method of sampling that involves dividing a population into a smaller groups, which is known as strata. The groups of strata are organized based on the shared characteristics or attributes of the members of the group. The process of classifying the population into groups is known as stratification. Now, we take up an example how this proportional stratified sampling is performed. We have three stratum, that is 1, 2, 3, and number of elements in the stratum is 200, 300, 500. Now we have to decide what will be the sample size. Suppose we take in the first item we take up as 10, in another we take as 50, and the third one we take as 25. Now we have to decide the sampling ratio as we have already discussed earlier. That comes 10 upon 200, 15 upon 300, 25 upon 300, 500. So individually that ratio comes out to be 1 by 20, 1 by 20 and 1 by 20 in all the three cases. And when we take this as a whole, that will be 50 by 1000, which will be 1 by 20. So mathematically we can say that n1 upon n1 is equal to n2 upon n2 is equal to till last one np upon np, which is equal to n upon capital N. Then comes your disposition stratified sampling. If the different strata in the population have unequal variances of the characteristics being measured, then the sample size allocation decision should consider the variance as well. It would be logical to have a smaller sample from a stratum where the variance is smaller than from the another stratum where the variance is higher. Here we will see if we have strata P and we have variances respectively, that will be sigma 1 square, sigma 2 square, sigma 3 square. Then the statistical efficiency is the highest when n1 upon n1 sigma 1. That means here it is being divided by sigma 1. And for the last one, it will be np upon nr sigma into sigma p. Now, the same data is being taken, and there are three stratums 1, 2, 3. Number of elements of each stratum is 200, 300, 500. Stratum variance is 2.25, 4, and 0.25. The stratum standard deviation will be sigma 1, that is 1.5 under root of variance. 4 is 2, and for 0.25 it is 0.5. Sample size will be, because here we have different sample size, 13, 26, and 11. And the sampling ratio will be 0.065, 0.087, 0.022. And overall, the next one is cluster sampling. Here we said we take up an example of a colony. Let this colony is being divided into 11 blocks from block A till block K. Cluster sampling is used in this situation by treating each block as a cluster, as you can see in the diagram. 2 blocks are selected out of the 11 blocks at random, and then the information is collected from all the families residing in these 2 blocks. What is the difference between cluster and strata? The strata are homogeneous within and different from other strata. Clusters should be heterogeneous within, and the different clusters should be similar to each other. A cluster is a mini population and has all the features of the population. The criteria used for stratification is a variable associated with the characteristics measured. Convenience of the data collection is usually the basis for cluster definitions. And there are very few strata, but there are many clusters. Multi-stage or multi-phase sampling. Multi-stage sampling is that where the sampling unit is something larger than from different populations. In other words, if we repeatedly collect samples of the same size from the population, compute the statistics, that is mean, standard deviation, proportion, and then draw a histogram of those statistics. The distribution of that histogram tends to have is called the sample distribution of that statistics. Now we will be moving towards the numerical component, so we have to understand what the theory part is all about. What are the different terminologies and what are the different symbols we will be using. We will start with sampling distribution of means and central limit theorem. Sampling distribution of sample means from a normal population. Let X be the sample mean of the random size of sample n drawn from a population having mean m and standard deviation s. In that case, the mean of x bar is mu x bar is equal to mu, and the standard deviation of x bar will be sigma x bar equal to sigma upon under root n. After selecting a sample, one would like to go for estimating the value of population parameter, testing a statistical hypothesis about the population, comparing two or more populations, and then performing correlation and regression analysis. Now comes sampling distribution. Sample statistics is a function of n samples value x1, x2 till xn. Sample statistic is a random variable and therefore has a probability distribution or a probability density function. In short, we call this as PDF. It is also known as sampling distribution of the statistic. Sample statistics from the basis of all inferences drawn about the populations. Probability distribution of the sample statistics allows us to calculate the probability that the sample statistics assumes a particular value. This ability to calculate the probability that the sample statistics lies in a particular interval is the most important factor in all statistical inferences. We are aware of that the samples denoted by x1, x2 till xn. Then sample mean will be sum of all, which is denoted by x bar, which is equal to sum of all the observations divided by number of observations. For another sample of size n from the same population, we might get a totally different set of sample values and so a different sample mean. There are many, perhaps infinite possible values of the sample mean. Now we will be talking about sampling from infinite population. Population is infinitely large. Population mean is given by mu, and population variance is denoted by sigma square, and sampling is without replacement. The standard deviation of sample mean is also called the standard error of the mean. And the standard error of the mean indicates the extent to which the observed value of the sample mean can be away from the true value due to sampling errors. Mathematically, what we have E is equal to E x bar is equal to mu, and variance of x bar is sigma square by n. If we talk about standard error, the standard error of the mean, that is sigma x bar, is equal to sigma upon under root n. This is standard error of the mean. Here, the population is finite. Population mean is mu, and population variance is sigma square, and sampling is without replacement. Then, random variables do not remain independent. What is the change? E x bar is equal to mu, and variance x bar is changed, that is sigma square by n into n minus n upon n minus 1. But when we talk in terms of standard error of the mean, that is sigma x bar equal to sigma upon under root n multiplied by under root n minus n upon n minus 1. This factor, under root n minus n upon n minus 1, is called finite population multiplier. Under normal condition, that is for sampling from normal population, if we have x tends to n mu sigma square, then it will follow x bar tends to n mu in and sigma square by n. The normal distribution is a continuous distribution, and so the population cannot be small and finite if it is distributed normally. Now we take up an example what we have discussed till now. Now we will be converting that theory into a practical example. Suppose the diameter of a component produced on a semi-automatic machine is known to be distributed normally with a mean of 10 mm and a standard deviation of 0.1 mm. If we pick up a random sample of size 5, then what is the probability that the sample mean will be between 9.95 and 10.05? Now, converting this statement into a mathematical notation, we can see that x tends to n, that is the mean, comma, standard deviation, that is 0.01. Then your x bar tends to 10, 0.01 by 5. We have to find the probability of the sample between 9.95 and 10.05. That means your mean, that is 10 mm, will remain in between, and it will be written as probability 9.95 less than equal to mean less than equal to 10.05. Now we will be changing this into the mathematical notation. That will be 9.95 minus 10 upon 0.1 divided by under root 5, which is less than equal to x bar minus mu upon sigma divided by under root n, less than equal to 10.05 minus 10 upon 0.1 divided by under root 5. When we will be solving this, we will be getting negative 1.12 less than equal to z less than equal to 1.12. Since it is symmetrical, on one side we have negative 1.12 and on the right side we have plus 1.12. So that means this is symmetrical. So we can write it as 0 less than z less than 1.12 multiplied by 2. The value of z at 1.12 will be 0.3686. We will multiply that by 2. We get an answer of 0.7372. That means the probability that the sample mean will be between 9.95 and 10.05 mm for a standard mean of 10 will be 0.7372. This is how under normal condition it is shown. Then comes your central limit theorem. If x1, x2 till xn are n random variables which are independent and having the same distribution with mean mu and standard deviation sigma, then if n tends to infinity, the limiting distribution of the standardized mean will be z equal to x bar minus mu upon sigma divided by under root n, which is a standard normal variate, and normally it is that a sample size larger than 30 is generally considered to be a large enough. We have to keep this thing in mind. Then comes your student t distribution. In actual practice, the value of population standard deviation sigma is often unknown, which makes it necessary to replace this with an estimate. Usually, S, the sample standard deviation is used. Now you can see that if we don't have the standard deviation in the problem, then it will be replaced by the estimated value of standard deviation. So we have the relation x bar equal to mu upon sigma divided by under root n, which is now replaced by x bar minus mu upon s divided by under root n. The exact sampling distribution of x bar minus mu divided by s under root n is given by t distribution. If x is a random variable having the standard normal distribution and y is a random variable having a chi-square distribution with new degree of freedoms, and if x and y are independent, then the random variable in terms of t is given by x divided by under root y by nu. Nu is the degree of freedom, which has a distribution which is known as t distribution or student's t distribution with new degree of freedom. There are many t distributions, each with its degree of freedom, which is the only parameter of this distribution. A t distribution is similar to the standard normal distribution, as we can see in the figure. It becomes flatter and wider and has long tails along them. If you remember, it is almost similar to normal distribution curve. That depends if we have infinity degree of freedom, the graph is more bell-shaped, and as the degree of freedom reduces, it becomes flatter downwards. As the degree of freedom increases, the t distribution becomes closer to the standard normal distribution, and when the degree of freedom becomes infinitely large, the t distribution and z distribution becomes indistinguishable. That's what we have done. In practice, we use x bar minus mu upon s divided by under root n. But what is the change here? Would have a t distribution with n minus 1 degree of freedom. It is therefore possible to know the sampling distribution of x even when sigma is not. This result is very useful when the sample size is not very large, and we have seen earlier if the sample size n is large, then the t-popul distribution with large degree of freedom can be approximated by z distribution. The t distribution is used when the degree of freedoms are not larger than 30. If the degree of freedoms are larger than 30, The t distribution is approximated by standard normal or set distribution. Sampling distribution of the proportion. If n is sufficiently large, p dash will be as n bracket p comma pq by n. This approximation works quite well if n is sufficiently large so that both np and n1 minus qp are at least as large as 5. Now we have to decide the interval estimation. Suppose we want to estimate the mean income of a population of households residing in a part of city. We might proceed by picking up a random sample of 100 households from the population and calculate the sample mean, that is the mean income of 100 sample households. But in the absence of any information, the sample mean can be used as a point estimate of the population mean. Lower the standard error of the mean, the greater is the confidence of the correctness of our estimation. This purpose is further refined in interval estimation, wherein we present our estimate as an interval and quantify our confidence so that the true population parameter is contained by the estimated interval. Then comes confidence interval. The probability that the interval estimate will contain the true value of the population parameter that is being estimated. Suppose if we say that 95% confidence interval for the population mean is obtained by spanning 1.96 times the standard error of the mean on either side of the sample mean. We mean that if we take a large number of sample size of size n, say 1000, and obtain the interval estimates from each of these 1000 samples, and then 95% of these interval estimates would contain the true population of the. Now we will see how to calculate the confidence interval of the population. Suppose it is known that weight of cement is being packed bags is distributed normally with a standard deviation of 0.2 kg. A sample of 25 bags is picked up at random and mean weight of the cement in these 25 bags is only 49.7 kg. We want to find a 90% confidence interval of the mean weight of the cement in filled. Now, in the statement itself, it has said that it is normally distributed and the standard deviation is 0.2 kg. Mean is stated as 49.7, but we have to find out the confidence interval of the mean weight in these filled bags. We have to determine sigma x bar, that is sigma upon under root n, or sigma is 0.2 and your n sample size is 25. That means 0.2 divided by under root 25, which is equal to 0.04 kg. Now, sample size is less than 30, so we will be using t distribution. That is, t distribution value is 1.645. Your x bar is 49.7 given in the problem. You're not having the mean, that is mu, divided by, you have standard deviation of 0.2 and n is 25. After solving this, you can find out that it becomes out to be mu is equal to 49.7 plus minus 1.645 into 0.04. This is what your answer is. Since we have already calculated it as 49.7 plus minus 1.645, and when we will be shifting it, so your answer will be when we're solving it. Your answer will be 49.63 and 49.76 with a confidence level of 90%. Now we have to find out the sample size. As a matter of practice, statisticians usually consider sample size of 30 or more to be large. They've already seen it. In the large sample size, a 95% confidence interval estimate for the population is given by x bar plus minus 1.96 sigma upon under root. Now we will see a sample size for estimating population mean. We assume that population distribution is normal and the population standard deviation is known. In such a case, the sample size required for a given confidence level and a required accuracy can be easily determined. Suppose we want to know the weight of cement in filled bags is distributed normally with a standard deviation of 0.2 kg. We want to know how large a sample should be taken so that the mean weight of cement in a filled bag can be estimated within plus or minus 0.05 kg of the true value with a confidence level of 90%. For confidence of 90%, we have x bar plus minus 1.645 times sigma upon under root f. We have already calculated the interval, which contains the true population value of 90% of the level. Now, we also want the interval of x minus 0.05 to x plus 0.05 should have 90% of confidence level, what your question says. Then what we will be doing? We will be using this relation 1.645 times sigma upon under root n is equal to 0.05. When we will be calculating n, so we will be getting n as 43.3. So we must have a sample size of at least 44 so that the mean weight of the cement in the filled bags can be estimated within plus or minus 0.05 kg of the true value with a 90% confidence interval. This is how estimation is done when some information is given to us and we have to find the sample size. Now we move to next unit, that is testing of hypothesis. Study a class of problem where the decision made by a decision maker depends primarily on the strength of the evidence thrown up by a random sample drawn from a population. To test a hypothesis, a statistical procedure is followed, and this procedure is known as testing of hypothesis. Now the thing is what is exactly meant by hypothesis? Hypothesis, or more specifically, a statistical hypothesis is some statement about a population parameter or about a population distribution. If the population is large, the hypothesis is tested on the basis of the outcome of the random sample. A hypothesis is a statement about a population parameter or about a population distribution. In any hypothesis problem, we are faced with a pair of hypotheses such that one and only one of them is always true. One of this pair is called null hypothesis and the other one is known as alternate hypothesis. The null hypothesis is represented by H0 and the alternative hypothesis is represented by H1. Now the question arises, what is meant by null hypothesis? The null hypothesis is called by this name because in many situations, acceptance of this hypothesis would lead to null action. Rejecting the null hypothesis leads to a change in status quo ante. If the population mean is represented by mu, we can set up the hypothesis as h naught is to mu is equal to 20. And your alternate hypothesis will be h1 is to mu greater than 20. What we have represented symbolically above can be interpreted to mean that the null hypothesis in that population mean is not greater than 20. Whereas in the alternate hypothesis, in that population mean is greater than 20. It is clear that both H0 and H1 cannot be true, and also that one of them will always be true. At the end of our testing procedure, if we come to the conclusion that H0 should be rejected, this also amounts to saying that H1 should be accepted and vice versa. Type 1 and type 2 error. If we wrongly reject H0, when in reality H0 is true, the error is known as type 1 error. Similarly, if we wrongly accept H0, when H0 is false, that error is known as type 2 error. Let us take a situation where a patient suffering from high fever reaches to a doctor. And suppose the doctor formulates the null and the alternate hypothesis as H0 is the patient is a malaria patient. H1 alternate one will be a patient is not a malaria patient. Then what are the different cases what they arise? Case one is suppose the hypothesis H0 is really true. That is, patient actually a malaria patient, and after observation, pathological and clinical examination, the doctor rejects H0, and that is he or she declares him or her a non-malaria patient. It is not a correct decision, and he or she has committed an error in decision known as type 1 error. Case 2 states that suppose that hypothesis H0 is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor rejects H0. That is, he or she declares him or her a non-malaria patient. That is a correct decision. Case 3. Suppose suppose the hypothesis H0 is really true. That is, patient actually a malaria patient, and after observation, the doctor does not reject H0. That is, he or she declares him a malaria patient. This is also a correct decision. But case 4. Suppose the hypothesis H0 is actually false. That is, patient actually a non-malaria patient, and after observation, the doctor does not reject H0. That is, he or she declares him or her a non-malaria patient. It is not a correct decision, and he or she has committed an error in decision which is known as type 2 error. Both these errors are bad and should be reduced to minimum. For a given sample size, these two errors neutralizes each other. If the testing procedure is designed and to reduce the probability of occurrence of type 1 error, simultaneously the probability of type 2 error would go up or vice versa. What can be at best be achieved is a reasonable balance between these two errors. Type 1 error is much more severe than type 2 error, and so we need to control it. Type 1 error generally results in financial losses to the company, whereas type 2 errors generally result in an opportunity loss for the company. Then comes your significance level. Probability of type 1 needs to be controlled, and this is done through specifying a significance level at which the test would be conducted or is conducted. The significance level therefore sets a limit to the probability of type 1 error, and test procedures are designed so as to get the lowest probability of type 2 error subject to the significance level. The probability of type 1 error is usually represented by the symbol alpha, and type 2 error is represented by beta. Testing of hypothesis suffers from the limitation that the financial or the economic cost of consequences are not considered explicitly. In practice, the significance level is supposed to be arrived at after considering the cost consequences, and it is very difficult to specify the ideal value of alpha. Probability of type 1 error should be lower, that is, the value of alpha should be lower. In practice, most tests are conducted at alpha equal to 0.01, alpha equal to 0.05, or alpha equal to 1 by convention as well as by convenience. Now, here we see what happens. Acceptance region, as you can see, is too big. We can say that it is at the level of 0.01, and we are studying about type 1 error. And the right side part, the part which is not considered or the part which is shown shaded, is the 0.05% on the other side. Often we accept a null hypothesis, rarely reject a null hypothesis even when it is false. This condition arises. When this condition arises, as you can see, this part has been reduced, and we can say that we are at the level of 50%, 0.25 on the left side and 0.25 on the right side. Here again, we are studying type 1 error. Here, we rarely accept a null hypothesis, and we often reject a null hypothesis when it is true. Now we take up an example how this is interference is drawn. Testing of a chemical. If wrong inferences is there, whole group of users will be poisoned. What we will do? We prefer high significance level, that is high probability of type 1 error, and we reject H naught when it is true. Another example, the free assembling of big machines. If wrong inferences is drawn, some parts may be repaired or replaced. We prefer low level of significance, that is high probability of type 2 error, and we accept H naught even when it is false. Here we are studying about effectiveness of a drug. H naught, it had no effect, and the alternate hypothesis states that it had an effect. And we are studying this at a level of 5% of significance. So for 5% of level of significance, we have mean plus minus 1.96 times of standard deviation. Negative will be on the left side and positive will be on the right side. At the center, it will be 0.95. This region in between is the acceptable region. This is a 5% level of significance, and accept means 5% of level of significance. Data does not allow us to reject a null hypothesis. Then comes your power curve of a test. Here we calculate the probability of rejecting H naught for different values of mu, that is mean, and plot these on a graph. Such a graph is known as power curve of a test. H naught, null hypothesis is H naught is to mu less than equal to 20, and your alternate hypothesis H1 is H1 mu greater than 20. When we are drawing graph, so we can see there are two lines. One is a thick line and the other one is a dashed line. Dashed line is for the H naught when x mu is greater than equal to 20.6, and we are rejecting H naught at x bar greater than equal to 20.5. The p-value of a test. The significance level is arbitrarily fixed. A better way of expressing the conclusion of a test is to state the p-value of the probability value of the test. P-value of the test expresses the probability of observing a sample statistic as extreme as the one observed if the null hypothesis is true. Hypothesis testing procedure. There are basically two phases in testing of hypothesis. In the first phase, we design the test and set up the conditions under which we shall reject the null hypothesis. Whereas in the second phase, we use the test based on the sample evidence and draw our conclusion as to whether the null hypothesis can be rejected, or else what is the p-value of the test. Now what is the procedure? What we do? Step one is state the null and the alternate hypothesis, that is H naught and H1. We choose the best statistics, that is the sample statistics that will define the critical region. Third step, specify a level, significance level of alpha. Fourth step is define the critical region in terms of test statistics. And step 5 is to compare the observed value of the test statistics with the cutoff value of the critical value and decide to accept or not or reject the null hypothesis. Why it is needed? Inspection sometimes does not allow inferences. Suppose a manager commits that average work efficiency is 90%, and our calculation gives a result of 95%, we accept, 40% we reject, and 89% we have to apply some thought. Intuition does not work, so one has to decide on the basis of sample information. Testing of population mean. Under different conditions, the test procedures have to be developed differently. There are many cases like when the population variance is known or unknown, when the distribution of sample size mean then Z can be approximated by a normal distribution, when test is two-tailed or one-tailed test. This is what we are discussing, that depending upon the problem given to us, when we have to draw the conclusion in hypothesis testing, these all things have to be kept in mind. Now, under normal distribution or tail distribution, depending upon if the sample size is large than 30, there are two conditions. When the population SD is known, we use Z test. When population SD is not known and the sample size is larger than 30, we apply Z test. When sample size is larger than 30, population SD is known, we use Z. But when population SD is not known, we use T test. Here are some conclusions. We are considering a case of bulb manufacturer. Two conditions are there: if life is short and life is very high. We reject If the life is short, that is, it is of bad quality, and we reject if life is very high, then large production cost. So here, what are the how the hypothesis is made? H naught is to mu is equal to mu H naught, and the alternate is H naught is to mu is not equal to mu H naught. These are the two conditions which come while we are drawing up the conclusion. Now, for the that was for the manufacturer. Now here for the bulb wholesaler, rejective life is shorter, that is of the bad quality, and accept who is bothered about what is that. See the change. H naught is to mu is equal to mu H naught, but here in this case, second part changes. H naught is to mu is greater than mu H naught. Similarly, its graph changes. That means the region changes, or in other words, the population probability changes. Now we will see how conclusions are drawn. We take up an example of wind manufacturers. Condition is it must withstand 80,000 kg per square inch, and its standard deviation is 4,000 kg per square inch, and its mean is 79,600 kg per square inch. The condition is very simple. Here n is equal to 100. H naught is to mu is equal to 80,000. That means it can withstand. And the alternate will be H1 is to mu is not equal to, that means it won't withstand 80,000. This alpha has been taken as 0.05. Now we have to evaluate standard error of mu, that is mu sigma x bar, which is equal to sigma upon under root n. We have already seen sigma is 4,000. Under root n will be under root 100. This comes, sigma x bar comes out to be 400. Now we have to calculate z. Z calculated will be equal to x bar minus mu h naught upon sigma upon under root n. Now how conclusion is drawn? If z calculated is less than z tabular, we have to accept the hypothesis. And if z calculated is greater than z tabular, we have to reject the hypothesis. We take up another problem. Here, the notations what we are provided to us are different. We are testing about the promotability of an employee. We say that H naught is roughly 80% are promotable. Committee finds out only 70% are promotable. Now what changes? N is 150, suppose there are 150 employees. PH naught is 80%. What is accepted? That is 0.2. The Q will be 1 minus P. That comes out to be 0.2. What is the population which can be promoted? That is 0.7. What the committee says, then Q will be 0.3. Alpha is equal to 0.05. We have to find out standard error of mean. That is sigma P bar is equal to under root P H naught Q H naught upon N. We have all the values. We find it out as 0.0327. Now we have to calculate Z calculated. That is P bar minus PH naught upon sigma P. If Z calculated is less than Z tabular, we will accept the hypothesis. And if Z calculated is greater than Z tabular, we have to reject the hypothesis. Or in a nutshell, we can say that if under any condition Z calculated is less than the tabular value, we have to accept the hypothesis. And if Z calculated is greater than Z tabular, it has to be rejected. So with this, we will be concluding today's session.